So this is in the area of analysis on fractals, and I know a lot of you are not in that area, so I will try to put a little potted explanation of how much you need, which fortunately is relatively small, in order to appreciate what is going on. This is joint work with Marius Ionescu, Okoudjou, and Bob Strickhartz in several different configurations. And I called the spectral properties of pseudo-differential operators on the Sierpinski gasket. Well, when I started trying to write down how to explain just a bit with the pseudo-differential operators in it, without explaining a few other things first, I discovered this wasn't really quite possible, so I had to stick some extra stuff at the beginning, and that's why there's too much material. So, the beginning of the story is 100 and odd years ago with the Szego limit theorem. So this is a theorem proved by Szego about multiplier operators on the unit circle. So we take some nice function f, it's positive c1 plus alpha, and you just consider the operation on the unit circle of, I'm going to project, maybe I do need a laser pointer. Which button was it? Laser, there we go. I'm going to project onto this collection of functions in L2. That's there. And then I'm going to multiply by f, that's my square bracket f operation. And then I'm going to project again. So this is basically just a matrix, in fact it's a turbulence matrix. Then I'm going to take the determinant, log of the determinant, normalize by the size of the matrix, and take the limit as n goes to infinity, and it turns out that the limit is this. And there's an equivalent formulation in terms of the trace. So this is a staggering theorem. Here is a marginally more general version, which is, but not so terribly different, also due to Szego. Basically what you do is you say, that operator that I said, project, multiply, project, take the eigenvalues, take a continuous function, evaluate it at the eigenvalues, average, then in the limit, you get this integral of f composed with your multiplier little f. Obviously, this theorem generalizes the previous one because the previous one was the version where you had log x. For the previous one, we needed that the function was positive because it was log. For this one, we don't. And you can think about this as saying that these eigenvalues have sort of the same distribution as these values f at, say, uniformly spaced points, because somehow the eigenvalues, or testing capital F at the eigenvalues is evaluating this integral. Yeah, so it's as if you were finding nice places to do a Riemann sum or something like that. So this is some staggeringly important theorem. There is a generalization called the strong-Szego theorem, which gives you an extra term in the asymptotic expansion. Barry Simon, who pretty much literally wrote the book, or more accurately books, on orthogonal polynomials on the unit circle, calls these theorems the most celebrated in orthogonal polynomials. I was reading this lovely paper of Estelle Besor and William Helton, where they pointed out that there's no that the operator theorists were just confounded by this theorem when they first saw it, because there's no reason why this determinant should even exist, right? Like, these things don't look like they should be determinantal class. And then, of course, they go on to explain why they actually sort of are modulus of commutators and so on. They've been used for all sorts of crazy things, like they're used to analyze the two-dimensional Ising model via Onsager's formula, right? So this describes magnetization. You sort of spin up and spin down, and you look for spontaneous magnetization. There's a critical temperature, and the behavior of magnetization in a critical temperature is computed bizarrely by actually strong-Szego limit theorem. That's why the strong-Szego limit theorem is proved. And then they've been proved for all sorts of classes of operators, and et cetera, et cetera. One particular one that I want to point out, because it has something to do with our, whoops, what did I do? With our pseudo-differential operator case, is this version due to Wiedem, who found spectral asymptotics of a pseudo-differential operator from its symbol using a sort of a Szego theorem. So no, there's no fractals yet, sorry, but we're getting there. right? So his motivation was to look at the eigenvalue distribution of a Schrodinger operator. So it's just minus Laplacian and then that multiplication operator again. Where here he was saying for a smooth function on some manifold M. And there was a solution by Mark Kack and I forget, Kack and Spencer. Anyway, for the two-sphere, and they used some expansion of Legendre polynomials, and it had this sort of Szego kind of flavor. And Spencer said to him, well, there should be some general Szego theorem that works. And indeed, he was able to prove that you could replace this multiplier operator with some sort of pseudo-differential operator and get a Szego theorem that gave you asymptotics of the spectrum. And so his thing looked like this. You've got spectral projections of the Laplace Beltrami. So that's, before we had spectral projections onto trig functions, I mean, e to the in theta kind of, which are just Laplace Beltrami for the circle, right? So his were Laplace Beltrami for a manifold. You ask that the rank of the projections goes to infinity. You take some zero-order pseudo-differential operator with some properties of the symbol, and then he got what is precisely a Szego-type theorem, where he's integrating the principal symbol over the unit sphere. Okay, so Victor Guillermin was visiting us one time, and he said, so you know all of these things about the Sierpinski gasket and its Laplacian and its spectrum. So do these Szego theorems work? And so we sat down and tried to figure it out. And indeed, the Szego theorems do work. And so we have both, well, at least the weak one. We have both the classical Szego theorem, and we have a pseudo-differential operator theorem now, Szego-type theorem, for the Sierpinski gasket, of which I've only drawn about 6 levels, but and I'll give you precise statements of those later. And the proofs are completely unlike any of the classical proofs, and I don't know how to make any of the classical proofs work, which probably means that there's something deeper going on that I don't understand yet. I thought for a little bit that maybe some variant of Wiedem's approach would work, but in practice, actually, no, I have no idea. So, what do I mean by these sort of theorems on the Sierpinski gasket? Well, that's where the analysis on fractals bit comes in. And so I want to view, the Sierpinski gasket as some sort of limit of graphs. So there's the m equals 0 graph, the m equals 1 graph, the m equals 2 graph, just so you have in your head what the picture of the graphs looks like. And then I'll call these little scale 2 triangles, say those are 2 cells, and I'll use this notation: x is a neighbor of y at scale m if the obvious thing, they're neighbors in the scale m graph, right? And then following Kagami's approach to getting the Laplacian on the Sierpinski gasket, I can do the following stuff. I can take graph Laplacians. So how do you take a graph Laplacian? Well, you're basically trying to take a second difference on a graph, right? Which is more or less just saying, take the difference on the edges that come out of a single point x and add them up, yeah? And then I renormalize. Now this is not the Euclidean normalization, and the story as to why it's 5 to the m instead of 4 to the m is a long story, and I'm not going to explain, right? But it's not the Euclidean normalization, but one renormalizes, and it turns out that for precisely this renormalization, these graph Laplacians, they converge as you take this limit of graphs, and you get a Laplacian operator on the gasket. And there's a corresponding collection of Dirichlet forms, which you should think of as like integral gradient squared. So I just take the difference squared on the edge of a graph and add them up over all edges of the graph. I renormalize appropriately, right? And again, the particular constant I have, the particular renormalization factor here is part of that story that I wasn't going to tell you. And you get convergence to a Dirichlet form on the gasket. And you are supposed to think this object is like Sobolev norm 1 derivative in L2, integral gradient squared, and this object is like Laplacian, and indeed they're connected if you use the usual Bernoulli probability measure on the gasket, so 1/3 on each level 1 cell, 1/9 on each level 2 cell, and so on. Then the bilinear form associated to this quadratic form by polarization, you have an integration by parts kind of formula where integral gradient u against gradient v, right, or for the correct notion being the notion from this Dirichlet form, is minus integral Laplacian u against v. And then one other little point that I'll need, for a notion of how smooth the functions have to be for the Szego theorems is that it turns out that if you take 2 points, then there is in fact a function which is 0 at one point and 1 at the other point, and is in the domain of this Dirichlet form. And more than that, there's a minimizer of the energies over the non-empty collection of such, and the reciprocal of this minimizer is a metric on the set, right? So it's called the resistance metric because of an analogy to electrical network theory. If you built a network on the fractal with these with resistances, basically 5/3 to the m, then measure the resistance between 2 points. That would be Rxy would be the number you get. So this is how one gets a Laplacian, right? And this Laplacian has many interesting properties, not all of which we need. However, we do need basically these ones. It is a self-adjoint operator, it's non-positive definite, and has compact resolvent. So it has this discrete spectrum, which is all negative numbers, and accumulates only at -infinity. What's more, there's an explicit description of all the eigenvalues using a certain one-dimensional dynamical system, and there's an explicit description of all the eigenfunctions, right? And which eigenvalues they correspond to and exactly how you build them. Yeah? So this is this slide summarizes some facts about eigenfunctions that we need. Specifically, our proof of Szego theorem is based upon the fact that these eigenfunctions actually have a property that's very unlike Euclidean eigenfunctions, namely that they're localized. Euclidean eigenfunctions of a Laplacian, of course, are analytic. Yeah? Analytic functions never have, say, compact support, right? But eigenfunctions of this Laplacian, due to basically some symmetry properties of the Sierpinski gasket, they are highly localized, or most of them are highly localized. So from these various references that I've put, one can say that if you look at the collection of eigenvalues of size less than some constant multiple of 5 to the n, then there are basically 3 to the n of them. They come in 3 types, which are called 2 series, 5 series, and 6 series for various reasons that, again, I won't explain. The 2 series have global support, but there are very few of them. There are basically 2 to the n out of these 3 to the n will be 2 series and will have global support. And so when I take limits in Szego theorem, they will make up a vanishingly small portion of the spectrum. So there'll be a small portion of my projection and they will disappear. The 5 and 6 series have a slightly more complicated structure. For each j less than n, there's what's called a generation of birth of the eigenvalue. And that corresponds to the size of the support. And so in this set of eigenvalues, for each j, there are basically 2 to the n minus j eigenvalues, whoops, typo, of each of it corresponding to each generation of birth. And each eigenvalue has a multiplicity basically like 3 to the j, because what you're doing is you're having eigenvalues that are born at scale j, and the corresponding eigenfunctions live on cells of size j, right? And there are basically 3 to the j cells of size j. Yes, 3 to the j cells of size j, and for various other reasons to do with the dynamical system, there are 2 to the n minus j such eigenvalues. All right. That is very useful for proving a Szego limit theorem, because remember the Szego limit theorem said project, multiply, project, and now take a normalized limit, right? When I do my normalized limit, anything that has large support is going to disappear because there are very few of them. And all the rest are highly localized. And if I project and then I multiply by a continuous function, and my projection basically lived on nice localized places, then that continuous function might as well be constant, right? It might as well just be little step functions. So that's the strategy of proof one uses. And in fact, then from 6 years ago, it turns out, Casso, myself, and Bob Strickhartz proved that if you have projection on eigenfunctions of eigenvalue less than lambda, and this is the number of them, and you normalize and you take the appropriate Szego quantity, then indeed you get a Szego theorem. And what's more, you get some step towards a stronger Szego theorem, because although we don't have the next term in the expansion, we do have a pretty good estimate on its size, right? One can generalize it in the same manner as I stated before for the classical Szego theorem, if I take the eigenvalues of this operator and then I look at evaluating f or averaging f over these particular choices of values, then this also converges to the integral of f composed of the multiplier little f. And one can think about this as an equidistributed kind of idea. I didn't precisely define equidistributed when I mentioned it with regard to the classical Szego theorem, but what I had in mind was that if I have two sets in an interval, and there are equally many points in these sets, and I look at, for any continuous function, evaluating f at one of the points and subtracting evaluating at the other, and averaging over the set, right? And then taking the limit, as I make the sets larger and larger, this will go to 0. And so we call this equally distributed, and we call it almost equally distributed if it's true for a subsequence of the n's. That should have been a subsequence nk, not jk, sorry. And so under the assumptions of the previous theorem, you can take a collection of points in the gasket itself such that their images under f are basically almost equally distributed to the eigenvalues of this Szego type operator. So I said that there had to be lots of bits before I could get to the pseudo-differential operator bits, but so some years ago, Marius, myself, and Bob Strickhartz wrote a paper about pseudo-differential operators on the Sierpinski gasket, and so I just want to give you a couple of really basic features of the theory. So you know the structure of the spectrum of the Laplacian. You take some normalized gasket crossed with 0, infinity, which is where the spectrum of minus the Laplacian lives. You're going to take the weighting px lambda n against the spectral resolution, integrate against the function, and call this doing px minus lambda ux. And of course, the simplest case of such an object is something like a spectral multiplier. Take a function, Fourier transform it, multiply it on the Fourier side by some fixed function, and then Fourier transform back. Right? If you have no x dependence, this is the Sierpinski gasket version of that. Right? Because I've just got, if there's no x dependence, I've just multiplied by something at lambda n, the spectral projection, and then I'm done, right? By summing back over the lambdas. But so this allows for some spatial variation as well. I think I skipped that because I don't critically need it. Okay. So then we want to consider the same sort of operator, one of these Szego type operators where we project, apply a pseudo-differential operator, and then project again. Now for the pseudo-differential case, okay? And so we needed to make some restrictions on our pseudo-differential operator, and here they are. So it's bounded, it's measurable. At each eigenvalue, it's continuous, and more importantly, if I run through the eigenvalues, then I have some uniform limit with respect to x. Then it turns out that all the eigenvalues live in some bounded interval, and one can prove a Szego limit theorem. If you additionally put a lower bound on everything so that it stays away from 0, then you can do a Szego limit theorem with a logarithm of a determinant instead of a trace or applying a continuous function. And so the previous results that I had with Casso and Bob are for the case where you actually don't have any dependence on the spectral side, right? You don't have any differential type operator. You just have a multiplier operator. Now, I should look at how much time am I on.
You have like 10 minutes maybe.
Yeah, awesome. Clearly means that I went too fast, but that means that you get to ask questions. What did I just do? So we had in mind applications of this, for example, to understanding something about eigenvalues of Riesz and Bessel operators, and indeed they work in this case. This is just a direct application of the theorem. And we also had in mind application to certain sorts of Schrodinger operators. So Schrodinger operators for which this is applicable, for example, are ones where you have a spectral multiplier which has a limit with respect to the frequency, and you have some continuous function on the gasket, and so direct applications of the theorem give you this. There was actually also a more interesting application for which I should probably draw something on the board, but so and that's why there was some previous work on this by Castle and Bob. So if I consider some Schrodinger operator where I have a continuous multiplier, like a continuous function to multiply by, and I have some continuous function of the Laplacian, which is eventually increasing on the spectrum, and more importantly, doesn't compress anything in the spectrum too much, right? Then when I look at the spectrum of this operator, so I can think of taking some blocks in the spectrum of this operator. There are some special places, some special locations along a particular type of sequence of as it happens, 6 series eigenvalues, but it's actually about some particular structure or about gaps in spectrums of eigenvalues here. But so there's some special sequence I can take, such that if I now look at my continuous function and I find its minimum and its maximum, and I look at little intervals of length minimum and maximum, and I put them at the appropriate places in the spectrum, right? These lambda j going off to infinity. And I look at what eigenvalues I get in there, and then I take all of these and I just translate them back to live on the same interval, right? Hence that translation somewhere there. So I look at these eigenvalues, I translate them back to live on the same interval, I put Dirac masses at each of them, and I average them out, and this is now a measure on this single fixed interval here. Then it turns out that using the Szego theorem, we can prove that these converge weakly to the pullback of just the mu measure on the gasket under the continuous function, right? So just the measure whose action on the whose action on a continuous function on the support of on the range of chi is just integration like this. So this is sort of a result about how eigenvalue clusters for these kinds of Schrodinger operators work, right? Asymptotically at least, because as you go out in these blocks, what you're seeing is clustering blocks that look increasingly just like this pullback measure. So I think I'll stop there and just let you ask questions. I trust that going too fast doesn't mean that you have too many.
So any questions?
Or of course too few. And
I have a question, not on these operators, but which fractals are limits of graph?
So in the sense that I was describing, I think I can go backwards. What makes this limit of graph idea work is that the things shouldn't be too connected. So what was special about these points on which we built the graph was, I need a pointy thing, was that these were points that disconnected us, right? So in fact, these 3 points here are critical points. These 3 that happened at the previous stage were actually post-critical points in the sense that so we have some finite collection of points, the forward images of which disconnect us at all scales, yeah? So the limits of graphs that you want, the fractal is a limit of graph idea that you want to use, and it works nicely at least for, say, post-critically finite graphs. So graphs for which there are a finite set of points that have this post-critical property that their forward images disconnect sort of everything at all scales. However, the question of when can you do something more like this is a considerably more subtle one. and is still not in any reasonable way resolved. So one knows some reasonably large class. If you have a lot of symmetry, then you can do this. So where a lot of symmetry means, for example, you have a fractal for which your post-critical set is made up of a bunch of fixed points. So your fractal comes from an IFS, and the post-critical set is made of a bunch of fixed points of the IFS maps. Yeah, and for every reflection in a hyperplane that fixes the post-critical set set-wise, right? So it just shifts these fixed points to one another. Yeah, the whole thing has to be invariant, right? So something like that, yeah, where you have like a very large symmetry group, then you can do things like this. But if you don't have so large a set, then you have to be more clever. Okay, then there's a deeper theory. All right, but not a complete one by any means. Other questions? Right, well, thanks very much, and thanks very much.